Good morning. Today I am going to discuss the production of rotating magnetic field in a three-phase induction motor. Let us see how RMF is produced in the three-phase induction motor. When you give three-phase supply to the stator, it will produce three fluxes R, Y, B. So I am taking R, Y, B phase sequence. So R phase flux is pi R, Y phase is pi Y, and pi B. Each phases are 120 degrees apart. So when if you take pi R is a pi m sin theta, so the next Y phase will start after 120 degrees. So after 120 degrees, Y phase will start, and another 120 means after 240 degrees, B phase will start. So this is the representation of fluxes produced by the line currents. Here, if you at I'm taking R as a reference phasor. So at this instant, at theta equals 0 degrees, we have Y phase flux and B phase flux. And if you take at this point, the Y phase flux is 0 and R phase flux and B phase flux are existing. And at this instant, the Y phase flux is existing and R phase flux is existing. Means at any instant on this line, one phase flux will be zero and another remaining two fluxes will exist. So because of this one resultant flux will produce. That resultant flux only we call as a rotating magnetic field. So first I'm taking different cases. So in the first case at theta equals to 0 degrees, I'm taking next 60, 120, 180 like that. At different cases I'm considering. Then how RMF will produce, we'll see. So at the first case, I'm taking theta equals to 0 degrees. So when you substitute this theta equals 0 degrees in these equations, so this will be 0. Sine 0 is 0. Sine of minus 120 is minus root 3 by 2 pi m. Sine of minus 240 is root 3 by 2 pi m. So after substituting theta equals 0 degrees, we will get these three relations. And similarly, if you substitute theta equals to 60 degrees, so 60 degrees in here, you will get these relations. And similarly, on more cases, 120 degrees. So you will get these relations. Now, after observing all these three things, in the first case, pi r is 0, two fluxes are existing. Second case, pi b is 0, two are existing. Third case, pi y is 0, and two are existing. So at any instant, one flux will be 0 and the remaining two fluxes will exist. So now for the first case, I am drawing the phasor diagram. So this is R phase, this is a Y phase, and it's a B phase. Each is 120 degrees apart. So all are 120 degrees apart. Now uh, pi r is 0. So here R phase is 0. So that's why its origin O I'm taking. So from here, and next pi y is minus root 3 by 2 pi m. So this is a positive direction of pi y. Negative means this opposite side. So this will be your pi 2 with minus root 3 by 2 pi m or 0.866 pi m. And root 3 by 2 pi m is B phase. So root 3 by 2 pm. So the phasor sum of B and C will give you the resultant flux. So this is your resultant flux OA. So that OA we can calculate the resultant flux we using this formula 2 pi cos alpha by 2. So where 2 the maximum flux value is root 3 by 2 pi m, and to cos alpha this value is 60 degrees. So cos 60 by 2 will give root 3 by 2. So after simplifying, we are getting 1.5 pi m. So this is your resultant flux. So if you for the second case also, if you draw the phasor diagram, you will get like this. So R phase is, this is R phase, Y phase, B phase. Here B phase is 0, that's why I did not mention here. So minus root 3 by 2 means this side, and this is plus root 3 by 2. So the phasor sum of these two will give you this OA, and again we will get the same 1.5 pi m. So if you third case also you will get the same answer, same as if you draw the phasor diagram. Here you will get the resultant OA or resultant flux in this direction for the third case. So this will be continuous as the waveform increases. If you see here, the first OA we are getting here, next case we are getting here, and third case we will get here. It means your resultant flux is moving in clockwise direction. So right side. So here first case, second case, third case, fourth case, like that. It is moving in clockwise direction. So that rotating magnetic field will produce, because of this resultant flux, the RMF will produce, that will rotate in clockwise direction with a speed of 120 F by P. So the RMF is rotating with a 120 synchronous speed in the stator field. So where F is a stator frequency or supply frequency. The supply frequency which we are giving to the stator, that will be your stator frequency. And P is your number of poles. By using this expression, we can find out the synchronous speed of the induction motor. Now next we are going to discuss the different types of induction motors. So according to the type of rotor, we have squirrel cage rotor and slip ring induction motor or wound type induction motor. These are the different types of induction motors. So this is looks like a cage, that's what we call as a squirrel cage rotor. And at the end of this one we have end rings. So these are short circuited end rings. So this side and this side we have short circuited end rings. These are the copper bars. So this is squirrel cage type rotor, and this is a wound rotor type induction motor, and it has slip rings on the shaft. So on the shaft we have slip rings. These winding terminals are connected to these slip rings with the help of brushes. So these are the different types of induction motors. Next, we will see the power flow in the induction motor. So, the how power stages, what are the different power stages in the induction motor? Let us see. So, when you give three-phase supply to your stator, so that is your net electrical input power you are giving to the stator. So, in the stator, we have stator losses. So, because of stator winding, some losses will occur in the stator. So, those are stator losses. And after that, we'll get some output. That is your stator output. That stator output we are giving to the rotor. So this stator output is nothing but your input to the rotor, that is represented with the P2. And in the rotor also we have some losses. There is a rotor copper losses represented with the PC. Here these rotor iron loss I am not considering. So only rotor copper losses. And after that we'll get some mechanical power developed in the motor represented with the PM, and this rotor is coupled to shaft. So there some losses, frictional losses will occur. So that those losses are called mechanical losses. So then after that we'll get some useful power or shaft power. So these are the different power stages in the induction motor: input power, stator losses, and stator output power, and the rotor copper losses, and power developed in the motor, and then frictional losses or mechanical losses, and finally the useful power or shaft power. So here we have the air gap power P2 and core loss power, mechanical power relations with respect to slip. We have these relations. We already have seen these equations. So by using these relations, you can find out the core loss or stator air gap power, or else the slip. So by using these relations, we can calculate any of the following. These already we used in the previous classes for solving the numerics.